Hey guys, this is Miss Scott, and I'm going to lead you through some notes on molar volume, which is a specific case for stoichiometry when we're dealing with gases. Okay, so this is a new conversion factor that we can use when we're dealing with gases at a particular set of conditions. Okay, and so what we're going to learn to do is kind of actually determine the liters of gas that are used or produced by a reaction, which is a really useful way to measure gases because it's a little bit easier than trying to figure out its mass. Okay, so the last slide of this slide deck has 3 practice problems that you're going to complete on your own below your notes. Okay, so make sure you set up a new page, Unit 6, molar volume notes with stoichiometry with gases. Okay, so let's actually go back to the beginning of our unit and think about Avogadro. So one of the ways that we kind of got to Avogadro's constant, our 6.022 times 10 to the 23rd, is because Avogadro actually hypothesized that equal volumes of all gases at the same temperature and pressure contain equal numbers of particles. So since the total volume of a gas occupies is primarily made up of the empty space between the particles, the actual size of the particles themselves is nearly negligible. Okay, so we haven't looked a ton at states of matter, but gas particles are very small compared to the large amount of empty space between them. They're moving really fast and they're really far away from each other. And so gases, more so than solids and liquids, can be affected by more easily affected by the conditions. And as set conditions, this hypothesis that Avogadro made turns out to be true. So the first kind of thing to know about gases is that they are compressible. Okay? And so that just means that you're able to actually change the volume of a gas by either compressing it or expanding it. And the main way we do that is by using pressure. So when we put a gas under high pressure, the particles are forced close to one another, and this decreases the amount of empty space and reduces the volume of a gas. If you decrease the pressure, the opposite happens. So as you decrease the pressure, those gas particles can spread out more and more and more, and there's going to be more empty space, and that's going to increase the volume of the gas. So this is actually what you see if you've ever taken like a bag of chips or something like that up into the top of the mountains. You have a lower atmospheric pressure as you go up in elevation, and so lower pressure leads to a larger volume for the gas that is inside that bag. Okay, just to kind of so you're aware, pressure is defined as normally a force per area, and so per unit area, and so that's just kind of to give you an idea of what this is measuring. We haven't talked much about pressure yet. Okay, and so our volume of gas is going to vary depending on what pressure conditions you have, whether or not it's higher pressure or lower pressure. My volume of my gas is going to change. And so that makes it kind of complicated when we're thinking about trying to calculate the volume of gas produced. My volume is also affected by temperature. Okay, so when you heat a gas up, the particles move faster and that gas expands. And so as you therefore that increases the volume that the gas sample takes up. So if you have like a low temperature, your gas is normally going to have a smaller volume. At a higher temperature, it's going to be a larger volume. If you've ever taken a balloon, if you put it in ice water, it's normally going to make the balloon shrink. The gas particles inside are going to start moving slower, and that volume is actually going to decrease. If you put it in hot water, the balloon should expand as those particles move faster and move farther away from each other. And so because of the variation in gas pressure due to pressure and temperature, because of the variation in gas volume due to pressure and temperature conditions, the comparison or calculation of gas volumes has to be done at standard temperature and pressures. So because if you change the temperature, if you change the pressure, you're going to change the volume of gas that is produced in a reaction. What chemists have decided to do is set kind of one standard temperature and pressure where they can accurately calculate the volume of gas that may be either used or produced during a reaction. And so because of these kind of variables, we have one set standard temperature and pressure. And so that set standard temperature pressure is called the standard temperature and pressure. It is abbreviated STP. Okay, so STP. And it is defined as 0 degrees Celsius and 1 atmosphere pressure. Okay, so 0 degrees Celsius is the same as 273 Kelvin. That's in a different units Kelvin versus units Celsius for temperature. And then our standard pressure is 1 atmosphere, which is generally defined as about the pressure at kind of sea level on Earth. However, there are other units of pressure, such as millimeters of mercury or PSI or kilopascals. And so this can be thought of as 760 millimeters of mercury or 101.3 kilopascals. But we're just going to, for purposes of this class, say that our standard pressure is 1 atm and our standard temperature is 0 degrees Celsius. Okay, so remember, because we have, when we vary the temperature or vary the pressure, that changes the volume of my gas. For all of our calculations, when we are calculating the volume of a gas, we are going to have to explicitly talk about gases only being at standard temperature and pressure. And so when they are at standard temperature and pressure, 1 mole of any gas will occupy exactly 22.4 liters of space. And so this is sometimes referred to as molar volume. Okay? And so 1 mole of any gas at these specific conditions, so at 0 degrees Celsius and at 1 atmosphere, will occupy exactly 22.4 liters of space. It does not matter the identity of that gas. So it could be helium, could be oxygen, could be carbon dioxide, could be sulfur trioxide. It doesn't matter how large or small those individual gas particles are. There will be exactly 1 mole of gas of 6.022 times 10 to the 23rd particles of gas in 22.4 liters of space at STP conditions. Okay, so remember, changing our temperature or changing our pressure will affect the volume of gas produced. Okay, that volume could either increase or decrease depending on your temperature and pressure conditions. And so this is only true, this conversion factor is only true for STP. And so we can think of this as basically 22.4 liters is equal to 1 mole of any gas at STP. So I can actually write this as 1 mole over 22.4 liters, or 22.4 liters over 1 mole. I'll wait for a moment for that black bar to go away. And there's so many of them. Okay. So kind of giving you another visual. If we think about helium, nitrogen, and methane as 3 examples of gases, in exactly 22.4 liters for each of them at a pressure of 1 atmosphere and a temperature of 0 degrees Celsius, each of these samples would have a different mass. So there would be 4 grams. If you weighed it, it would be 4 grams for the helium, the helium gas inside that container, be 28 grams for that nitrogen, or 16 grams for methane. However, you would have the same number of gas molecules inside that 22.4 liters. So even though the mass is different, you have the same number of particles. Okay, and so Avogadro's hypothesis states that equal volumes of any gas at the same temperature and pressure contain the same number of particles. And so at a standard temperature and pressure, 1 mole of any gas is going to be 22.4 liters. And this is a pretty powerful conclusion to draw, because we can now, if we kind of set our reactions to happening at standard temperature and pressure, calculate the volume of gas, so the liters of gas that are either used or produced by a reaction. So if we come to our stoichiometry roadmap, you have on kind of either side liters of gas at STP, and our conversion factor here of 22.4 liters over 1 mole. So I can either start with liters of gas and calculate grams or liters or atoms or molecules of another substance in my chemical reaction, or I can start with maybe grams or moles, and I can calculate the liters of gas that may have been produced by my reaction. So let's take a look at 2 example problems. So our first example problem using molar volume, so molar volume is my 22.4 liters equals 1 mole, is what STP volume of CO2 will be produced when we burn 34.0 grams of methane. So couple of things just to note. One, for any problem where you are calculating the volume of a gas, you need to make sure it says STP. If it does not, then you cannot assume that your 1 mole is going to be 22.4 liters. Okay, so it needs to say STP in the problem. Other thing, make sure you know whether or not you're calculating the volume of a gas or volume of a solution. We're going to look at solutions next week. So make sure that you are thinking about gases and not just and not solutions. Okay, so if I look here in my problem, all of these are gases, and so I'm calculating the volume of carbon dioxide gas. Okay, so what am I given? I have 34.0 grams of methane. And I know that I'm trying to find the volume of CO2 at STP that is produced. So here is using my stoichiometry roadmap. Here's kind of the pattern that I can draw. I'm given grams. I can use my molar mass to figure out the number of moles of methane. Then I can use my mole ratio to get from moles of methane to moles of CO2. And then I can finally, if I know my moles of CO2, I can use this new conversion factor in my molar volume to determine the liters of CO2 produced. So let's take a look at what this looks like. So I've got 30.4.0 grams of CH4 of methane that I'm starting with. I'm going to first use my molar mass to convert to moles. So my molar mass is 16.05 grams of methane for every 1 mole of methane. And now I know moles of methane, so I can convert to moles of CO2 because that's what I care about. So based on my chemical reaction, there's no coefficient in front of methane or CO2. So I'm going to assume that they're both 1. So 1 mole of methane will produce 1 mole of CO2. And now I'm going to use my molar volume. And so I know that I'm at STP, and I know that 1 mole of CO2 will be 22.4 liters. Okay? And so if I multiply and divide by each, what I'm going to get is my 34 grams of methane will produce 47.4 liters of CO2. So let's look at a second example. Okay. What mass of water is produced when 25.1 liters of CO2 is also produced at STP? So take a moment, pause the screencast, and try this problem on your own. So hopefully you had a chance to try this problem. Let's take a look at how we're going to get from my liters of CO2 to grams of water. Okay. And so again, if I look at my stoichiometry roadmap, I'm starting with liters of CO2 and I'm trying to get to grams of water. And so the pattern that I'm going to use is I'm given liters, I can use my molar volume to figure out how many moles of CO2 that is. Then I can use my mole ratio to figure out how many moles of water were also produced. And then finally my molar mass to figure out how many grams of water that is. So you should have started with 25.1 liters of CO2. Using my molar volume, I can convert this by saying 22.4 liters of CO2 are equal to 1 mole of CO2. And so now I've converted into moles of CO2. Using my mole ratio, I can look at those coefficients in my chemical equation. It's going to be 1 mole of CO2. I'm also going to have 2 moles of H2O that are produced. And so now my final conversion factor is molar mass. And so I know that the molar mass of water is 18.02, And so 1 mole of water is going to be 18.02 grams. And so if I multiply and divide across, I should get 40.4 grams of H2O. So 40.4 grams of water were produced when 25.1 liters of CO2 were produced. Okay. So these were 2 examples of how to use molar volume as a conversion factor. So what you're going to do is try these 3 problems on your own. Okay, so you're going to complete them below your notebook. Okay, my advice is to open up the slides so that you have them in front of you. And you are going to need to write a balanced chemical equation first for each problem. So you'll notice each of these problems doesn't give you your chemical equation, but it does give you information about what your reactants and products are in that reaction. Okay, so your first step, write a balanced chemical equation for that reaction, and then solve for whatever it is you need to find. Okay, so you're going to try these 3 problems in your notebook, and we will go over them in class next week.